Hi, my name is Inês Lourenco and I'm from KTH in Sweden, and this work was done in collaboration with Rodrigo Ventura from IST in Portugal and Wahlberg, also from KTH. The title of our work is Teaching Robots to Perceive Time, a Twofold Learning Approach. And during this presentation, I'll show you what we've done in this paper. So to start with some motivation, we can start by thinking about all the amazing abilities that robots have nowadays. They can jump, cook, they can fly, dance, open doors, and even play soccer, and many more. However, these are all mostly biologically inspired. So you can see that we tend to want robots to do actions similarly to the way that humans and animals do them. However, there are still some problems. And besides the actions, the thought process behind how to plan these actions is very different still. So we can think about some challenges that still exist here. And for example, when it comes to experiencing the flow of time, perceiving synchronization, understanding duration, and so on, all these are related to time perception. And all these have a big impact in, for example, communication. So when it comes to time perception, robots and humans are still very different. Robots use their clock that is independent of all their other functions and function based on this clock. While humans, on the other hand, have a varied sense of passage of time. So they estimate time differently when they're older. In different situations, the sense of time is also varied. For example, we say that time flies when we're having fun. And so here we can see a problem, for example, that someone is complaining that their Google Assistant is interrupting them before they finish talking. And other problems can be that without this variable sense of time perception, these kind of robots are not able to adjust to the pauses in conversation, for example, according to the person that they're talking to or to the situation that is happening, while humans can. So the question that we pose in this paper is how can biologically inspired mechanisms of time perception be replicated in a cyber-physical system, such as a robot? And some motivation for this is that you can see, for example, in this paper, the authors say that in the field of robotics, the key role of time in cognition is not adequately considered in contemporary research. And this fact significantly obstructs the development of high-level robotic cognitive skills. And in another paper, the authors say that, however, despite the crucial role that sense of time has in our daily activities, the capacity of artificial intelligence to experience the flow of time remains largely unexplored. So there's many papers that focus on why it is important to give robots this sense of time, and that is why we pose this question. This is what we try to study in this paper. So we start by defining time perception in the following way, by saying that it is a subjective experience or sense of time measured by someone's own perception of the duration of events. In summary, you can simply say that it is the ability to perceive the passage of time and the duration of events. There are many definitions, but this is the one we use here. So unlike robots that have this clock, we don't have that. So actually time has been studied to be present in multiple brain areas. So there isn't a single one responsible for encoding time. So this is the case of basal ganglia, cerebellum, and the cerebral cortex that you can see in this image. And also this sense of the passage of time is influenced by many variables such as the emotional state, the attention, and the task difficulty. And lastly, the time perception is not only present in humans, but also in many animals, such as fish, mice, flies, and so on. So during this presentation, we'll start by presenting the framework we created to answer the previous question. And then we go into the two main components of this framework, so the external timing and the internal timing. Finally, we present an algorithm to show how the framework works, and we conclude with some numerical results and conclusions. So let's start with the framework. We start by considering that the perceived time stems from two different sources. The first one are external environmental stimuli. So these are basically stimuli that are collected by our sensors or the robot sensors. And it has been studied that the stimulus length influences a lot our perception of time, such as in this paper in the footnotes. And the second time source are internal neuronal processes. So here, what happens is that even if our sensors are off, like when we're sleeping, we can still estimate the passage of time. So, for example, time has been shown to be coded in the spiking activity of our neurons, as in this paper in the footnotes here. So our agent basically combines these two time sources. The first one we call external timing, and the second one internal timing. And what happens is that this external timing block is going to receive some observations, y of t, and estimate the elapsed time during the time while it received the observations. And then the internal timing block is going to use this time estimate to perform some actions. So this is a complete framework. It's a reinforcement learning framework where the environment produces these observations to be used by the agent, and the agent performs some actions in the environment and receives the rewards and the next states for which the environment evolves. So now you can see here on the left bottom corner that we're going to start by talking about the first component of the framework, so the external timing block. So the problem we pose here is, given some observations O collected from the environment, how can we estimate the interval duration? That is, estimate the elapsed time that we call tau. So this sensor data from which we collect the observations can be images from a camera or time series from a LiDAR or etc. And what happens is that we receive these observations O as a sequence of signals Y from M different sensors. And this is done during the interval t0 to t tau. Here on the right, you can see an example of a robot from IST in the simulator, so where we can collect observations. And in this setting, then we have a temporal discrimination task because we have a certain time interval, and our goal is to estimate the length of this interval that is started by a stimuli and stopped by another stimuli. So how do we do this? To estimate the elapsed time, we consider a Bayesian model that combines an innate sensory-based estimation of duration that is based on the probabilistic expectations of stimulus change, which is called the probability of seeing some observations given that some time has passed, with a prior information about timing mechanisms. Our goal is to estimate the maximum of our posterior distribution, which is a probability of a certain time having passed, given that we saw some observations. And the maximum of this distribution is going to give us the most probable time to have passed. So we basically want to compute our maximum a posteriori. However, we know that if we consider the prior as being uniform, which we're going to do here, then this maximum a posteriori becomes the maximum likelihood estimate, where this is our likelihood. So we can start by writing this term as a joint probability of these Gaussian functions with zero mean and a certain covariance. In this case, this is the expression that we get for the joint distribution, and we have to study what is our covariance function. This is our unknown, and it is parameterized by theta. So now the question is, how do we model this covariance function or the kernel? So to do this, we consider that environmental information does not change randomly, but shows high patterns of high correlation in both space and time. This has been studying in some papers that the time natural images vary according to certain rules. So, for example, in this paper, you can see that they consider that the kernel represents the difference in how much, for example, the pixels of an image varies from one time instance to the next. And so it has been shown that the Ornstein-Uhlenbeck process, or covariance, is the one that better defines these natural images. So the kernel is in this case given by this expression, And you can see that these lambda and sigma are the hyperparameters of the model. So what we do in this external timing block is we receive these observations, model them as according to these Ornstein-Wahlberg processes, and estimate the hyperparameters lambda and sigma. And then using them, we can estimate the maximum likelihood estimate of the previous expression. And from that, we obtain tau hat, so our estimates of the elapsed time. And now this estimate is going to be fed into the next block, which is the internal timing block. So what happens in this block, or the main question we pose, is how can we use this tau hat, the estimate of the elapsed time, together with some internal neural mechanisms to perform some actions. So to do this, we have to start by considering how can we replicate these internal neural mechanisms. And something very important that we need to consider is the dopamine neurons, because these dopamine neurons have for a very long time been known to be involved in action selection and reward prediction, and also more recently in interval timing. The reason is because they encode a certain reward prediction error. So this basically measures the difference between the received rewards and the rewards that was expected. This error became very used in temporal difference learning models. And so these are the models that we're going to consider here in order to replicate this behavior. So with temporal difference learning, we're going to start by using Q-learning because we are interested in the actions that we are going to perform. And we're going to use function approximation because it's what helps us if the state space or the action space are too large. We can simply consider that the state is given by a combination of features. So in this case, each state is described by D features that are called X that encode the animal's cognitive and sensory experiences. And these features are multiplied by certain weights omega, according to this expression. And now the question that comes up is how can we model these features? So for this, we're going to use something called the microstimuli framework because it has been shown to be the most consistent in terms of features with what actually happens in the brain. So the microstimuli features are a multiplication of trace height, h of t, that you can see here, with some temporal basis functions f. And the multiplication gives a series of decaying microstimuli, which encodes how much time has passed since the onset of the cue, for example. So it gives us already an idea of how the neurons work or the firing rate of neurons works. So this is our framework. And now we're going to then pass to the experimental setup. So we are going to consider or to base our experiment in an experiment done by the Champalimaud Foundation that is mentioned in this paper in footnotes. And the experiment consists of mice that can press three buttons: a short button, a start button, and a long button. And what happens is that once the mouse presses the start button, after a while it receives two tones separated by a certain time interval. And their goal is to classify whether this interval between the two sounds was short or long. And they receive a reward according to whether they got it correctly or not. So we time the mice start learning how to perform these experiments. And we, in this work, then replicate these experiments in this reinforcement learning framework. So we consider that our state is given by, state space is given by these three states: the init, the tone, and the interval, which you can see here. So before the mouse presses the start button, we are in the init state, then we hear a tone, and finally there's a sequence of interval states according to how many intervals pass between both, and then another tone. And then the action space consists of the start, pressing the start button, not pressing any button, which is the wait, which the mouse or the agent should do between the two tones, and then pressing the short or the long button in the end according to the interval duration. And then the mouse receives the rewards, negative if it fails, and that's how learning occurs. So the algorithm that we use for this is the following. we start by initializing all our Q values for all states and actions to 0, and we initialize the weights randomly. And then for each episode, so from every time that the mouse presses the start button to the end where it chooses how long the sound was, what we do is we initialize the initial state, which is the init in this case. And then for each time step, many things can happen. So if we just heard the first tone, we update the features according to the microstimuli. So we place microstimuli exactly at that time step. And then during the time between both tones, we collect these observations y of t. And when we hear the second tone, what we do is estimate the elapsed time according to these observations collected, and we update once again the features that have been decaying from the first time during this interval. And so based on all the features, we can compute the Q values. And then in this reinforcement learning framework, we take the action and observe a reward given and what is the next state that we go to. And then in the TD learning framework, the temporal difference learning, we start by computing, or we have to compute this reward prediction error and also the next weights. And then finally observe what is the next state that the environment goes to. And we do this until we reach the terminal state where the reward is given. And that is it. And now we can talk about some numerical results, and we're going to combine them already with some conclusions. So the first numerical result that we can see is that the elapsed time was successfully computed from environmental data from this external timing block. So in this figure, you can see that there are a set of interval durations that have been increasing, and this is our estimate interval duration. So you can see that as the interval duration increases, on average, we still have a pretty good estimate of the time that has passed using this external timing block. So we are able to, on average, compute the elapsed time. However, it is important to notice that the covariance has been increasing, so with the interval duration. But it increases in a linear way, and this is called a scalar property, which is also something that our brain, human and animals' brain, show, because basically when we are presented with an interval that is longer, it's harder for us to estimate it. So the second conclusion here is that uncertainty in the estimation of the interval duration from data increases with the length of the interval, exhibiting the scalar property. The next numerical result shows us that as learning occurs, so as the episodes start increasing, in the beginning we have a very big TD error when the reward is given, which is in this moment. So we are not expecting rewards, so there is a big difference between the expected and the received. But with time we start expecting it more until the moment where the TD error goes to 0, but we start having some error in the second tone. So we start predicting that the reward is going to be given even before seeing it. And this is called a conditional stimulus, and it's something that happens in the brain. So the conclusion we can take is that the error of the TD model replicates the firing rate of dopamine neurons, decreasing with reward expectancy. And finally, we can see that if we have a certain interval, it's harder for the mouse or the agent to classify the intervals that are in the middle between a short and a long interval, as you can see here. And this is exactly what happens in mice. So in mice, there is this orange curve. And the curve of our robot is quite similar, the psychometric curve. So this was that study in this paper also with the experience that I mentioned. So we conclude that, uncertainty in the classification of intervals is higher on the boundary between classes, and the psychometric curve of our agent closely matches the one of mice. So to conclude, we proposed an algorithm for providing temporal cognition to agents that combines two timing sources, which are external stimuli and internal neural mechanisms. And finally, in numerical simulations, we show that the agent that is using our algorithm is able to succeed in time-dependent tasks because it can show a similar, or it shows a similar way to perform tasks similar to that of humans and animals. And for future work, we plan to try out this in a real robot and maybe improve a bit our model. So thank you. If you have any questions, let me know.